Hello students, welcome to my class. Students, the first topic that we will see today is area vector. Now, a question that we face a lot of times is whether area is a scalar quantity or a vector quantity. So students, area is a scalar quantity, or you can say area is a scalar. But area vector, if I say area vector, then it is a vector quantity. So students, area is a scalar quantity, but area vector, if I say area vector, then it is a vector quantity. Clear students? Now, let us consider these as a planar element. This is a planar element whose area is delta S. Clear students? Now if we write area vector, then obviously we should explain about its magnitude and its direction, because a vector has magnitude and direction. So what is the magnitude of this area vector? This is area vector. So what is the magnitude of this area vector? It is the area of the element. What is this? This is a planar element whose area is delta S. Now what is area vector? Area vector is a vector whose magnitude is area of the planar element. And what is the direction of this area vector? It is normal to the plane. What is n cap? N cap is a unit vector which is basically representing the direction of area vector. Now what is the direction of this n cap, or you can say what is the direction of area vector? It is normal to the surface. Clear students? For example, this is a planar area. Now it's up to you which normal do you want to take. If you wish, you can take this direction, or if you wish, you can take this direction. Both are normal to the surface. Clear students? So for a planar area, area vector is a vector whose magnitude is area and direction is normal to the surface. Clear students? Now what is the need of this physical quantity area vector? Students, with the help of area vector, a lot of topics, or you can say with the help of this concept area vector, explaining different topics of physics becomes easier. Clear? Now let us take a closed surface. For example, sphere. This is a closed surface. Now this sphere is closed as well as it is carved. This sphere is closed as well as it is carved. So we will take a small area, or you can say a small element. Its area is ds. A very small element whose area is ds. Now what is ds vector? It is area vector associated with this area whose magnitude is area of this small part. Clear students? And what is the direction? Students, it is not only normal to the surface, it should be outward drawn normal. So students, for a closed surface. For a closed surface, the normal should be outward drawn normal. Clear, students? For example, if you take this as the direction of normal, then it will be wrong. The direction should be outward. The direction of area vector should be outward. Clear, students? Clear? Students, now we will see a very important topic. It is electric flux. Students, the word flux is basically related to flow. The word flux is basically related to flow. Now, what is electric flux through a surface? What is electric flux through a surface? Or what is electric flux through an area? Students, it is basically the amount of electric field lines. The amount of electric field lines, or it is basically the measure of the amount of field lines, electric field lines passing through a given area, or flowing through a given area, or you can say piercing a given area. Students, first of all, it must be clear that, for example, this is an area. Then if an electric field is going like this, if an electric field line is going like this, then only I will say that it is piercing this surface. Clear, students? And if it goes like this, then the electric field line is not piercing this surface. If it goes like this, then it is piercing this surface, and if it goes like this, then it is not piercing the surface. So students, what is the electric flux through a surface? So it is basically the amount of electric field lines piercing that surface, or you can say it is the amount of electric field lines passing through that surface. Clear, students? Or you can say it is the amount of electric field lines flowing through that surface. Clear, students? So to give you a better idea, I have taken an isolated positive charge, and these are the electric field lines of this isolated positive charge. Now I have taken two area. One is this one, another is this one. Clearly you can see that more number of electric field lines are piercing through this surface in comparison with this area. If I take this one, this blue one, and this one, clearly we can see that in comparison with this, more number of electric field lines are piercing through this one, through this blue surface. Clear, students? Or you can say that electric flux through this surface is greater than electric flux through this surface. Clear, students? So I hope the idea of, or the concept of electric flux is clear. Clear, students? So from the definition itself we can understand that electric flux is a scalar quantity. What is the definition? It is the amount of electric field lines passing, or amount of electric field lines piercing through a given area or through a given surface. Clear, students? So it is the amount of field lines. It is the amount of field lines. So obviously it is a scalar quantity. Clear, students? Now students, we will see what are the factors on which electric flux through a surface depends. So students, I have taken a region of uniform electric field. You can see the parallel lines. So this is a region of uniform electric field, and I have placed two planar areas. Clearly you can see that electric field through this surface, or electric flux through this surface is greater than the electric flux through this surface. That means greater the area of the surface, more will be the electric flux through that surface. Greater the area of the surface, more will be the electric flux through that surface. That means electric flux through a surface depends on the area of that surface. Now again, I have taken a region of uniform electric field. Now you can see that the electric field lines are very much dense. That means I am considering this electric field is much more stronger in comparison with this electric field. This electric field is much more stronger in comparison with this electric field. Now let us consider that the area of this surface is A and area of this surface is again A. Clear? Students, clearly you can see that electric flux through this area is greater than the electric flux through this area, because this region of electric field is strong. That means the electric field lines will be much more dense, or you can say the electric flux through this area will be much more than the electric flux through this area. Clear, students? That means the electric flux through an area, the electric flux through a surface also depends on the strength of the electric field. Clear, students? Also depends on the strength of electric field. Clearly you can see that in this region the strength of electric field is more in comparison with this region. So here both are of same area. Both the surfaces are of same area, but electric flux through this surface is greater than electric flux through this surface. So students, so far we have seen that electric flux through a surface depends on the area of that surface and also depends on the strength of electric field in that region. Clear, students? Now let us see one more thing. Let us consider that this is a planar area and this time electric field is not passing normally. Electric field is not passing normally, or you can say that, let us consider that electric field lines are inclined to the normal by an angle of theta. Electric field lines, yes, this is a region of uniform electric field, but electric field lines are not passing normally. They are making an angle of theta with the normal to the surface. Now let us try to simplify this figure. I am taking again this surface only. This is the same surface and I am representing the electric field with a single line. Clear, students? I am representing this entire electric field with a single line and it is passing through this surface making an angle theta with the normal to the surface. This is the direction of normal to the surface. Now students, let us break this electric field into its components. Let us break this electric field into its components. In this direction it will be E sin theta and in this direction it is E cos theta. Clear, students? So I have broken, or you can say I have resolved this electric field into two rectangular components. One is E sin theta, another is E cos theta. Now students, clearly you can see that E sin theta component is not piercing. It is moving. This is the surface. This is the surface and this is how E sin theta is passing. It is not piercing, students. It is not piercing. or you can say it is not passing through this surface, but E cos theta is piercing. E cos theta is piercing. Clear, students? So clearly again we can see that yes, it also depends on this value of theta. Or you can say if electric field lines are passing through a surface, then it is E cos theta which is basically piercing. It is basically E cos theta. It is E cos theta which is piercing. E sin theta is not piercing. Or you can say it is E cos theta which is contributing to the electric flux. So combining all these factors, we can say that electric flux through a surface, which we denote by phi suffix E, electric flux through a surface is equal to area of the surface than E cos theta. The students, what is theta? What is theta? Theta is the angle between the direction of electric field and normal to the surface. What is theta? It is the angle between direction of electric field and normal to the surface. Or instead of saying normal to the surface, you can say area vector. You can say theta is the angle between electric field and area vector. Clear, students? You can also write this formula as E vector dot delta S vector. Students, obviously you know about dot product or scalar product. So E vector dot delta S vector is equals to magnitude of E vector, that is E, magnitude of area vector, that is area of the surface, and cosine of angle between electric field vector and area vector. We know that direction of area vector is normal to the surface. Clear, students? And from here also you can say that electric flux is a scalar quantity because it is dot product of two vectors, or it is scalar product of two vectors, and we know that scalar product or dot product gives scalar. So electric flux is a scalar, and from the definition only you can say that electric flux is a scalar. It is the amount of electric field lines passing through a given surface or piercing a given surface placed in a region of electric field. Now students, we will see some special cases. So this is the case that we have seen already, where a planar area is placed in a region of uniform electric field, where electric field is passing through that area, making an angle theta with the direction of normal, or you can say with the direction of area vector. Then electric flux through that surface is given by E vector dot delta S vector, or you can write E delta S cos theta, whereas delta S is the area of this planar area, E is the magnitude of the strength of the electric field, and theta is the angle between electric field and normal to the area. Now this is special case number 1. In this case, again this planar area is placed in a region of uniform electric field only, but this time the entire electric field, or you can say the direction of electric field, is along the normal only. Is along the normal, or you can say it's along the direction of area vector. So clearly you can see that here the value of theta is the angle between electric field and normal, but here electric field is parallel to the normal, so theta is 0 degree. That means electric flux through this area, it will be E delta S cos of 0 degree, and we know that cos 0 degree is 1, so it is equals to E delta S. Clear, students? Now let us see one more case. Let us consider this as any arbitrary area, and it is placed in a region where electric field is not uniform. This is an arbitrary area, and it is placed in a region where electric field is not uniform, and we need to find the total electric flux through this surface. Now what we'll do, we'll take a small region. Let us consider this as ds. We have taken a small region, or you can say a small element of area ds. Now for this small element ds, obviously electric field will be uniform. For this entire area, the electric field is non-uniform. But for small element ds, electric field will be uniform. So let us consider that this is the electric field, or you can say uniform electric field for this small element ds. And let us consider that this is ds vector. This is ds vector, or you can say this is the direction of normal to this area element. Clear, student? So obviously for this small area we can apply this formula, because for this small area electric field will be uniform. So for this small area, the total electric flux through this small element is d phi equals to E vector dot ds vector. Clear, students? Similarly, we can find total electric flux by adding electric fluxes through this small elements. So what will be the total electric flux? You can say it's integration of this small fluxes, or integration of this small flux through small elements. What is integration? It is basically addition only. So total flux is the, you can say, addition of total flux through this entire area is equal to addition of, integration is basically addition of small fluxes through small elements. Obviously we can add electric flux because it is a scalar quantity. So it will be equals to integration of d phi, you can write E vector dot ds vector. Clear, students? Now if this arbitrary area is a closed surface, now let us consider this as a closed surface. It is a closed surface. For example, it is a cube. For example, it is a sphere. Then similarly, just like this, we need to find electric flux. We need to find electric flux through a small area, then integrate, then we will get the total electric flux. But here in integration, we give this circle kind of shape. So what does this shape implies? This means surface integral. This means surface integral, or you can say it means you need to perform the integration over the entire surface. You need to integrate it over the entire surface, or you need to add it. Integration is basically addition. You need to add it over the entire surface. What does it mean? It means surface integral, closed surface integral. That means while integrating or while adding electric fluxes, you need to take the entire surface. Clear, students? Clear? So these are the cases. Now what will be the SI unit of electric flux? So from here only we can find SI unit of electric flux. SI unit of electric flux will be, what is the SI unit of electric field? It is Newton per coulomb. What is the SI unit of area? This is area, right? It's meter square. What is SI unit of cos theta? Cos theta is a trigonometric ratio, and trigonometric ratio doesn't have any SI unit. So it is dimensionless, or it has no unit. So what is the SI unit of electric flux? It's Newton coulomb inverse meter square, or you can say it's Newton meter square coulomb inverse. Clear, students?